So hi, I'm Richard Biener from SUSE, and today I will try to give an overview over the vectorizer and its implementation with the purpose of enabling you to contribute to it. So first, I want to outline what I want to talk about. It's actually a lot, and it's kind of circular. So basically, independent of where I start, it's going to be missing pieces. And eventually I will get to the missing pieces that depend on the stuff I'm already talking about. So feel free to interrupt me in between and ask questions. It might be that I refer to a later portion of the talk, but it's also very likely that I can answer the question because it's about something that I wasn't planned to cover. Because of course the vectorizer is too big and 1.5 hours isn't enough to thoroughly explain everything. So I want to start with a short overview of how a user interacts with the vectorizer, so the programmer, and how a target would do that, both of which is not really the topic of the talk, but I think it's good as an initial introduction to basically what the vectorizer provides for users or for a target. Then I want to give an overview of the features of the vectorizer. It's probably going to be features of vectorizers in general, but specifically in this case, what GCC vectorizer can do. Then I will very briefly outline the source code structure of the vectorizer, like where you will likely find portions of the vectorizer. And then the main part of the talk is basically around how the vectorizer works, what kind of data structures are there, and then how it works again, because then we get into highly cyclic dependencies of all of the information. And in the end, I will very briefly cover the transformation phase. So this is basically vectorizer operation up to the decision what we are going to vectorize and how, but not actually emitting the code, because that's the very easy part. But I will still get to that, because there's part of it is also not so easy, but it's not really the area where a contributor would start to do anything. If you're not Tamar, then of course you will try to fix all that code. And at the very end, when you're doing something in the vectorizer, you're going to break stuff. So you need to somehow figure out what went wrong. And so that contains actually only very few hints. So in the end, it's going to be sitting down in the debugger and figuring out what goes wrong. But there are some helpers in the vector code and also in GCC in general that will help you with this. So let's start with the first part, which is how do users interact with the vectorizer. So ideally, the users don't know about vectorization and they just compile with O3 or even just O2, and the important code will get vectorized and it will be magically fast. That's what we would like the compiler to behave, but in reality, that's not always going to work. So a very good hint to any user who's interested in actual performance, so not all applications are good vectorization targets. So your program has to have several hot kernels that actually can be vectorized for it to be a target for that. What helps is when you use profile-guided optimization, because then you can tell GCC what part of the code is actually important. This later helps also to filter out the help you get when it's on some of the next slides. When you use there's the -opt-info flag, which you can use to tell GCC to tell you which loops it vectorized and also which loop it didn't vectorize. And if you use the profile-guided optimization, you won't get the noise from all the unimportant stuff GCC didn't vectorize, but it helps narrowing that down. So, especially when you use only O2, which enables the vectorizer, but only in a very limited way. So the vectorizer refuses to do things that cause a lot of code growth. You can, in addition, enable the vectorizer, which switches the cost modeling back to the default cost modeling, basically. And then you get the same behavior as if you were using O3, but just for the vectorizer part. And of course, something that's easy to be missed, especially like on the various popular architectures like x86 and ARM, when you're sticking with the base ISA, it's very likely that you can't make use of advanced vectorizer features like early break vectorization, because you do need advanced ISA support. Like on x86 today, every CPU you can buy has at least AVX2, but it's not enabled by default. So you have to remember, oh, I want to enable AVX2. So what you can also do is not rely fully on the compiler, but annotate your source. There are only very few pragmas in GCC that you can use to guide the vectorization. In particular, you can now tell GCC to not vectorize a particular loop, because it happens that vectorization can make code slower. For example, if GCC completely misguesses the number of iterations of loops, and you can hit the case where you have all the overhead of actually deciding whether it should vectorize or not. Even if it computes at runtime that it's never going to be profitable and always executing scalar code, you still pay the price for this overhead, right? So PGO helps to avoid that, but it's also easy to annotate loops with no vector. Then there's the second pragma, which is the IVDEP, which we actually borrowed from the Intel compiler, which had this like 30 years ago already. It basically tells GCC that in this loop, there are no forward data dependencies. So basically, you are free to unroll and interleave all vector iterations, all the scalar iterations, right? Because very often, the compiler cannot statically decide that the writes you are doing to some memory do not alias with the reads. The vectorizer will happily insert runtime checks to ensure this, but those come at a price. And if you have lots of these, you will run into some internal limit, which you can also up. That way, I think it's currently that we do a maximum of 18 such checks. But the number of checks is actually quadratic in the number of different data streams you have, because you have to check each stream against each other. So when you know there is no data dependence, you can tell the compiler with the IVDEP pragma, or you can use a restrict annotation on function parameters, or you can annotate loops with the OpenMP SIMD pragma. Actually, so the question is, when you use restrict, do you need the IVDEP? When you restrict in GCC works only when you can put it on function parameters, which restricts the restrict usage to some extent. And the IVDEP pragma is applied to a loop. So when you know something about a specific loop instance, then it's like more fine granular that you can use the pragma on the loop. But of course, it means that all of the memory streams are independent, right? So you can't have half of them dependent in some way and half of them not dependent. Yes. Then you would have to resort to restrict again. And of course, you can use obviously non-alias memory, for example, by using restrict, or by making sure to not use indirect accesses like via pointers, but have global arrays or make sure the compiler sees the allocation side where it can derive from when the pointer comes from a malloc, that it's obviously not aliased to something else. And in a lot of cases, the opt-info vec, when you add -mist, will tell you something. So I must admit that the -mist output is not very optimized or tuned or cared for. It's basically spitting out parts of what you get in the detailed vectorizer dump file. But in most cases, it hints at the very first issue GCC hits when it sees a loop and cannot vectorize it. So the line number referenced by the opt-info is usually the line number of the loop header. Like when you have a for loop, it's the line of the for. And so it's quite easy to correlate the messages to source code.
So the use non-wrapping IVs, Vitimet says you should always use signed integers for your loops, right? Unsigned integers wrap, right? And that's a problem. Or are there other problems that cause wrapping IVs?
Yeah, so the third point is use induction variables that are obviously not wrapping.
Right.
Like if you have an unsigned iteration and you start from 10 and go to n, the n might actually be less than 10.
Oh, yes.
You might not think of that, but the compiler has to.
Yeah.
So then it would cause one wraparound, and the number of iterations is no longer a affine function, and we use the affine analysis, the scalar evolution analysis, to determine how the memory stream behaves as a stream. And when we fail to do that...
But if you always use signed integers for your iteration thingies, it never causes problems, or does it sometimes?
Yeah, so when you use signed integers in C and C++, when there's an overflow, you are subject to undefined behavior, which means GCC can assume there's not undefined behavior. But you have the additional issue that like on 64-bit systems, if you use an integer, and this is used as part of an address expression, that you get promoted to unsigned long, and that you get that problem reintroduced. So it's actually there is no good other workaround when you actually hit that in the code than to try using a signed or a wider signed induction variable in that case.
Do you consider assume macro or assume futures where you can assume it's like less than such and such or more than such and such? Does that solve it currently? Is that supported?
So the scalar evolution analysis does use the value range information if it's present. So yes. So that was basically about how a user interacts with the vectorizer. So let me try to cover what a target maintainer has to do to enable vectorization for a target. So in principle, the vectorizer only relies on the machine description of the target. Like the vectorizer checks the opt tab, like for the add opt tab, whether it's implemented for a vector mode. So in principle, it's enough to implement instruction patterns for vectors. But that means at the first step, you need to expose vector modes to the middle end, while there's your target star.modes definition file where you add vector modes, basically look into example targets like ARM or x86, 64, and see how this generally works. So if you do not have a special target like with the variable vector length things, then it's quite straightforward what to do. Then the vectorizer, apart from the instruction pattern, it relies on a set of target hooks to enable the vectorization itself. There are, of course, default implementations for most target hooks that do something. So you should get vectorization, but you can tune how the vectorizer behaves by overloading some of these target hooks. So I've put in 2 links to the internals manual. One for the this is for the target hooks, and one for the standard pattern names. The latter is unfortunately not sorted in any way, so you have to basically go over the 2000 item list and find those related to vectorization. But as said, you start with the general pattern names, like for the bit operations, for the standard integer arithmetic or floating point arithmetic, because those are basically the same, just for vector modes. So important vectorizer target hooks are the auto-vectorize vector modes hook. It basically tells the vectorizer which vector modes to consider when vectorizing. That's used in a context of vector sizes to use, or modes with completely different behavior, like when you have ARM neon and ARM SVE, right? If you have a target that has just a single vector width, like PowerPC only has, or I think PowerPC has, or it's only 128 bits. So basically, it would just have a single vector mode to iterate over. And likewise, the preferred mode is basically the first one the vectorizer will try when vectorizing, which is for a simple target with just a single vector ISA. It is just the single vector mode. So in these cases, the default implementation would work just fine. Similar is the related mode hook. It basically, when you select one of these modes that the target returns here, then the related mode hook should return the vector mode of that same class, but for a different element mode and a different number of elements, but of the same class. So basically, you put in a SVE mode and you get back an SVE mode and not a neon mode, for example.
If you have a floating point mode, you can get an integer mode of the same size, or not?
Yeah, so if your like preferred sim mode for the loop is
Right.
A 2-element DF mode,
Right.
and the hook asks you for an integer mode with 4 elements, then you return the appropriate thing.
Okay, it can be different number of elements. Okay. Yeah. Wow.
Yeah, so it's not really about floating point versus integer. It's about classes of mode. Like on x86, you have the SSE modes, which basically tells the vectorizer the vector width to use, or the AVX or the AVX 512. On ARM, you have neon and SVE, and many more in the actual hook, but somebody else has to explain you why and why that's useful. RISC-V is similar. They also have gazillions of modes to iterate over for reasons. The other important hook is when your target can do masking on vector operations. For example, even just do a masked load or a masked store, then you need to implement the get mask mode hook, which basically, for any vector data mode, it has to return an appropriate mode to be used for masking of operations on that mode. Right? To make an example, for example, on AVX 512 on x86, the mask mode is an integer mode. It's like DI mode or SI mode, depending on the number of elements of the vector mode you put in. But with SSE, it's basically you get back an integer mode, an integer vector mode of the same width. So like when you pass in the two-component float or the two-component double vector mode, you get back the two-component DI mode, integer mode, because that's how AVX does masking. Right? It depends on the ISA. So the vectorizer supports everything that was implemented. It's basically the classical data vector modes and integer mode kinds. And like ARM and RISC-V, they use the vector BI mode. So there's a special BI mode that's underused in GCC, but it's used for that. Basically, a vector of bits, but x86 chooses an integer mode for that, which is also a set of bits, basically. And yeah, another important hook is the vec_perm_const hook. Permutes are very important for vectorization. With permutes, you can implement standard interleaving schemes, which basically date back to the very early ideas of doing vectorization. And the vec_perm_const tells the vectorizer what kind of permutes the targets can do. Because of not all ISAs, especially x86, have like a permute instruction that can perform any possible permute, but there are restricted operations. And I think it took until SSE4 or whatever, until there was a byte permute that is fully capable of doing all possible byte permutes on a vector. And that was slow then, of course. And there's a hook to drive the vectorizer costing. There's also a default for that, a default implementation. So that's not something I would tackle when enabling the target first. It's also some of the more complicated and intricate areas of the vectorizer that's hopefully going to improve soon or later. Yeah, so nowadays we have the create costs hook, which basically is supposed to instantiate instead of the vectorizer costs class, but the target can derive from that class, and so it has to instantiate the derived type. So it's C++y, basically hooks in hooks, but that's what we are doing now. And this is basically the old one, which is still used, where the hook gets a set of, I think it's 6 or 7 classes of vector operations, and the target is supposed to give a magic number describing the cost of that. And the first mechanism is much more complicated or much more powerful and much more confusing. So back to the optabs. There is, of course, the corresponding permute optab to the permute const hook. So the permute const hook tells the vectorizer this constant, so compile time known permutation can be implemented by the target, and then the vec_perm optab has to succeed expanding. Basically, all of these patterns are not allowed to fail expansion. That means the vectorizer first checks they are implemented. And so when the target implements them, it has to support the expansion. So it can't fail. So usually there are patterns in GCC that may fail, and when there's a fallback, so there is no fallback for all of these patterns, which means once we commit to using them in the vectorizer, the target has to implement them. There are quite a bunch these days of instruction patterns that are not of the standard kind that are also implemented for regular scalar integers. For example, we have separate patterns for vector compare. They are separate because they produce the previously mentioned mask mode as a result, right? So every compare of two objects will produce the corresponding mask output. And there's the vcont mask optab, which basically is a C conditional operation, and the first operand is this kind of mask. So it's basically a blend, right? So you can see it as a vector blend with a mask produced by, for example, a comparison. Then we have lots of optabs for loads and stores. So these are just two examples. Is the mask load and the mask store optab, which also receive a mask as one argument and the usual location of the load or the store and the data to store as operands. There are more variants of these. There are variants of the standard arithmetic patterns with cont added in front, which means that those are the masked operations. Like when you have floating point, you can have traps on some lanes. So if you have those executed conditional in the scalar loop, the vector loop will have them masked if the target supports it. Yes?
Do you have a way to handle, you were saying like you have to unconditionally either support that optab or not support it, but do you have any situations where like depending on the operand you might support it or not, like if you were, I don't know, trying to initiate a vector by some constant but you're only allowed the constant to be within certain, or an immediate but only within certain values?
So yeah, for constant generation, So for the constant generation, I think there's another hook.
Okay, so
and for some of these patterns, it's documented that we also consult the predicate for the operand. Like I think now all of the masked operations also have an else operand, because I mean, what value is produced when basically the mask bit is not set, and the target, and there are basically three standard values the vectorizer uses, like 0, merge masking, previous value, or don't care, and those are magic values, and the predicate in that case is used to tell whether the target supports one or the other variant.
Okay, thank you.
So these are the optabs, and on RTL you see whatever the target does in the expander, and on Gimple the vectorizer will basically put in internal functions that are called the same as the optab itself, apart from the permute, which has a tree def, it has a vec perm expression, so it's visible as vec perm expression and not as internal function call. But like the mask load and store, those are function calls in Gimple. And on RTL, they get transformed to whatever you chose to. Like you usually see a lot of unspec uses in the cases of masking and loads and stores, because there are often details in the ISA that are not fully visible to GCC. So that was the quick, not so quick introduction. I have to speed up. Let's give a quick overview over what loop vectorization in general does, and in particular, in this case, for GCC. So GCC can basically prepare the vector loop body by peeling a few first iterations to have the vector accesses in the main vector loop aligned. And it can also peel off remaining scalar iteration to an epilogue. Like when your number of iterations doesn't divide the number of vector lanes you have, then you have to somehow deal with the rest, right? And GCC can do this peeling either by applying masking in the vector loop or by emitting a scalar loop. Yeah, we can we can basically avoid all of the prologue and epilogue by using masking on the vector loop itself, which is especially important for the variable length vector operation. We can, when there is a scalar epilogue, we can vectorize that epilogue, for example, with a smaller vector size, considering x86 with its 3 vector sizes like 512, 256, and 128. We can do this twice. We have the main loop with 512, first epilogue with 256, the second epilogue with 128 vectors, and then a last scalar epilogue if it's still necessary. The vectorizer can do versioning. So what that means, it makes a copy of the loop before vectorizing it and conditionalizing the execution of the original scalar loop or the set of vectorized loops based on first some magic cost function, which is usually based on the actual number of scalar iterations of the loop. So basically we compute, it's only profitable when the scalar loop iterates at least 10 times. And otherwise we will fall back to the scalar version. And with that check, it's also checked like when you have the runtime alias issues, all these alias checks are performed. And some targets do not support unaligned vector accesses. In that case, there might also be a check of the data alignment requirements. And if any of these are not fulfilled, then well, you get a scalar loop. We can do outer loop vectorization, which means we have a loop nest of depth 2, but basically an outer loop and an inner loop. And the outer loop is the loop that is vectorized, which means the inner loop has the unroll factor of the outer loop number of copies and is virtually fused and interleaved, right? So basically all scalar operations in the inner loop are simply one-to-one replaced with a vector operation. Of course, we have to prove correctness of that transform. It's basically unroll and jam and then vectorizing of the result. Then, for not so long, we can do vectorization of loops with more than one exit. And all but one exit can be non-counted. And of course, we can vectorize loops when there is control flow inside the loop, when we can if convert that into masking operations. That, of course, depends on the target being able to do any masking. Like PowerPC can't do any reasonable masking. Yeah, so it seems to be a quite new feature. But I hope they will catch up. At least Sega convinced me PowerPC will become great. Then we can, of course, vectorize reductions. And of very many forms. And that's one area of the vectorizer that I won't go into any details. And we can also do quite efficient vectorization when you have partially or fully unrolled loops, like when you have the outer loop and the inner loop is fully unrolled, then you have like several accesses to the same data stream, but spaced with constant offsets, for example. Or this is called like super level word parallelism, and we can handle that just fine, usually. Oh, yeah, and we can, of course, also vectorize when there's no loop, when there's just a function, which means GCC actually does whole function vectorization. So we analyze the whole function and look for obvious opportunities, like groups of stores that are continuous in memory. Then we check, oh, maybe what we actually store can be vectorized. Or when there is use of the general GCC vector extension and you build up a vector of scalars, we check, oh, can we actually vectorize that vector build? And we can also vectorize reductions that way. But so I've not yet seen much cases where that actually helps performance. It's more like it's a feature that kind of naturally falls out of all the infrastructure we have. And it's, of course, nice to present. Okay, so you want to contribute to the vectorizer. Where do you start? You start with something you want to do, a problem, of course. But then there are very many files in the GCC repository. They unfortunately all start with a tree dash. So they do not order very well. But luckily, all the vectorizer things continue with vect. So you can glob by that. And there are actually not many files. I think they're becoming too big, so maybe we should make them more and split them up. But so the main API is all in tree-vectorizer.h. So we only have a single header file. So not like in other parts of GCC where we try to match up the location of the declaration with that of the definition. So we only have a single header file, which I think makes it easier to discover pieces. But you then have to grab where the actual implementation sits. So most of the time, the name will give you a hint, but it's also as often wrong. So in the tree-vectorizer.cc, you have some general utility functions for some kind of data structures, and also the main Gimple pass structure and main execute function, the pass itself. So there are actually two vectorizer passes, one for loop vectorization and one for the non-loop vectorization. Then we have the tree-vect loop. You can guess there are loop vectorization related function in that, like, for example, analysis of reductions and transform of reductions, basically everything that's special to loop vectorization. That's what's supposed to be there. The tree-vect SLP is a little bit more complicated. You will hear this SLP name very often during this talk, starting from now. And while generally in the academia it means superword level parallelism, I will refer to it in terms of the data structure that the vectorizer internally uses, because since last year, everything is SLP in GCC's vectorizer. So even not superword level parallelism thing in the vectorizer is still using the SLP data structure. So you will find all stuff related to that data structure in this file, and you will also find all the functionality for the superword level parallelism in this file, and for the basic block vectorization, which is basically for the basic block, you only have superword level parallelism because you can't form groups by unrolling, right? So this is why it was traditionally there. So this is one place we could possibly split up the thing and move the data structure related stuff into a different file. Then we have the tree-vect-data-ref.cc, not to confuse with the tree-data-ref.cc. The tree-vect-data-ref.cc is basically handling all of the load store analysis and also parts of the transform, but not the actual load and store operations. Then we have the tree-vect loop manip that does loop transforms, like the peeling, the versioning, induction variable related stuff in And in all cases, what is special there for the vectorizer or the implementation that was done for the vectorizer. So it's in GCC you often have like 2 or 3 implementations for like loop copying, and the vectorizer also has one of those, and these are in this file. Then you have the tree-vec patterns. There is the scalar pattern recognition. I will tell about patterns later. Then we have now the tree-vec SLP patterns, which is basically pattern matching on the SLP data structure, but also in that context always dealing with super word level parallelism, because that's the whole point of having the SLP patterns separate from the scalar patterns. And then we have the other kitchen sink thing. It's the tree-vec statements. There's basically all the general operations that are not especially loopy, all the analysis of operations and transform, and a lot of support routines for that. Like there you will actually find how to analyze loads and stores and vectorize them. So related to the vectorizer, not in the vectorizer pass itself, is the tree if conversion pass, which nowadays only performs if conversion for the vectorizer. So any other if conversion happens on RTL or in the phi-opt pass, but not in the if conversion pass. You can, I think you can still enable it manually to get loop if conversion on non-vector code. But when operated for the vectorization, the if conversion pass always creates a copy of the loop and if converts that copy, and only if that is vectorized later is the if converted form actually used. But it's a separate path. Then you have the tree data ref, which is basically the general GCC data reference analysis and dependence analysis, which the vectorizer uses. And you have the scalar evolution code, which does induction variable analysis, which is important for data reference analysis. So let's dive into the vectorizer. So here I have put 2 examples of a loop with actual super word level parallelism. So I'm accessing a struct. Right? I'm multiplying each element of the struct by s and have an array of that thing, and I'm iterating over the array indices. On the right-hand side, I have a similar thing for the whole loop vectorization, where I see a reduction of data that's from a load. Right? So these are 2 prime candidates for vectorization. So how does it work? So the vectorizer starts in the pass vectorize. The execute function basically loops over all loops in the function. It does then the try vectorize loop. Then for each interesting vector mode, that is the vector modes returned by this auto vectorize vector modes hook. Right? So for each of those modes, it tries to analyze the loop. Analyzing, I will go into more detail what that does. Basically, it decides, can I vectorize it? And in the end, it decides which mode to use. The target does that. And then it transforms the loop. And then it goes to the next loop in the function. Quite easy. And the whole function vectorization works basically the same. We do have to split the function into analyzable regions. Ideally, we can analyze the whole function, but like when you have some ASM statement in there we can't handle, or computed goto or exceptional control flow, we basically stop, and we then split the function into single entry, multiple exit regions, because those are nice kind of to analyze. And for each of those regions, again, we are iterating over the vector modes. We analyze the region and check whether any of the subgraphs we analyzed there are profitable, and then we'll eventually vectorize them. So at that point, we still decide whether we want to go to the next mode or not, right? So we still compare something, but once we figure out there's at least one profitable subgraph we want to use with that mode, we stop. So because we can't really handle the case that we have two different of the modes and then vectorize with them. That's basically a structural issue how we handle this iteration. So like on x86, there is this kind of iteration, but it will stop at the first mode where there is any kind of success. Right, so it will never compare costs between SSE vectorization and AVX, for example, because it will start from the widest mode and goes to lower, and the widest is always going to be better than the lower. So that's the theory, at least. So for example, ARM, they're really doing a lot of work to compare the different things. With some success, obviously. Yeah, so when we are like costing, applying costing to a loop vectorization, we are relying on the backend with the vector cost class to get us a cost of the overall scalar loop and of the overall vector loop. It can work as simple as just summing over individual vector statement costs, but it can also like take into account, oh, I have a loop and there are 20 vectorized shifts and only one load, and I only have one shift unit. That's not going to be fast. So it can do advanced analysis like that. And so the target does the summing for us, and we rely on the magic number to be bigger or smaller than scalar loop cost. And the vectorizer itself will add cost for the prologue and epilogue copies of the loop, and will have a good guess at the cost of these like versioning conditions that are always executed to then compute this magic number of scalar iterations that has to be at least present until the vectorization is profitable. And that's actually, so this single check against the scalar iterations is performed first, and you get an immediate branch on that. So at least the overhead of doing that should be usually small. But of course, you get all the code there, and possibly code layout issues, as later the basic block reordering usually thinks the vector code is going to be hot, the other one is cold, so it gets put into the cold section. And so if you never hit the vector code, you are probably getting some kind of back and forth jump, which may be costly in some cases. But there's the no vector pragma as a rescue if that happens. So let's move on to the analysis phase. So what I try to do here, before you get scared, is on the left side you see what the loop vectorization does, and on the right side you see the other way around. Yep. On the left side you see the basic block vectorization flow, and on the right side you see the loop vectorization flow. You will notice that there's a lot of overlap. For example, both analysis phases start with analyzing all the data references in the code region. Then the basic block analysis goes on with analyzing the data ref accesses. That's basically doing an extended analysis on the data references. So after we figured out, we can actually analyze how the data reference behaves. The access analysis will try to relate different data accesses. Like on the source example I showed before, we had 3 elements of a struct loaded. So it will correlate these 3 loads and say, well, they are a group. And there's basically, this is the distance between the elements and stuff like that. This is the analysis of the data ref accesses. Then, so on the loop side, we have that here. On the loop side, what we do after the data ref analysis, we analyze scalar cycles. So we look at, in Gimple, at the phi nodes in the loop header and try to detect reductions, inductions, and things like that, and classify them. And we do this scalar pattern recognition at that point. And as these two interact somehow, we have to fix up the scalar cycles with what we did with the pattern recognition, and then we continue with the data ref accesses. On the basic block vectorization side, we then search through all the statements for those related statements, like the group stores or the vector construction, from where we start then the greedy build up of the SLP graph. So I have to refer to some future slide, SLP graph, data structure. So we check for those roots. Then we also do the pattern recognition, because there's no good reason for the particular ordering in that case. But we also have to fix up, because patterns are somehow special. And then we do this SLP discovery. On the loop side, before we go to that, the SLP discovery, we are marking statements to be vectorized, which is basically classifying each statement in the loop on whether it is maybe an unused statement, a statement that's not really important to vectorize, like it's an induction variable increment, or an induction variable that's only used in a data access. Right? So we don't need to vectorize those, because it's basically computing the address of the vector load is done from scratch. It's not done by vectorizing the address computation, because we still only need one address for the vector load. Right? So it decides which of the statements are relevant for the vectorization. There was this one. And then for loop vectorization, we are at that point analyzing the dependencies of the data references in the loop. So we basically compute when there is no dependence, everything is fine. When there is a dependence that we don't know about, then we schedule that for this loop version runtime check. Or if there's a dependence we can see, like if we see, oh, this iteration accesses the same data as the previous, the iteration, 10 iterations before, then we basically compute the maximum unroll factor we can use without hitting that dependence. Right? So, and then we do this SLP discovery. There's a whole slide about that later. Then we have this function called make SLP decision. I've apparently not yet removed it. Yes?
Hi, so you've got these two streams of, I assume they are hooks or functions running in parallel somehow in these slides. Are they in parallel? What's the workflow there, sort of?
So they are actually not hooks. On the left side, you see the function, I think it's called BB SLP analyze region, and on the right side, it's the function vect analyze loop _2, and it's basically the flow how the analysis for loop and basic block vectorization happens. So I just wanted to cover both with the same thing to make the point that, well, it's actually the same, apart from details, of course, like basic blocks do not have reductions that we can vectorize.
Thank you.
Yeah. On the right side, you can see after the SLP discovery, I made a red line and put in a VF there. So at this point, we commit to a specific vectorization factor. So that's the unroll factor of the vector loop. That's an important thing because it constrains what vector modes you can use. It constrains how many actual vector statements you are going to emit for a single operation. And so it influences all the costing. So after you commit to that, and it influences what kind of permutations you will eventually need, and you need the fixed modes to ask the target if it can vectorize the permutation. Right? So after that, after we nailed down the vectorization factor, we have this optimize SLP phase, which basically it tries to get rid of permutations, like by pushing them down and up from loads and stores, and see if when you merge them, they vanish. That's very nice if they do, right? And we do the same on the basic block vectorization side, right? Then we have this gather SLP loads. This is just a data structure walk and filling up some array. Then we analyze the alignment of the vector accesses that is there, because only after we know the vectorization factor and the vector modes we want to use, we can actually make an educated guess about whether they are aligned or not, right? On the loop side, we then go over the set of runtime alias tests we have registered and try to prune them with extra information, but also by like removing redundant tests. And at that point, we then eventually give up when there are too many tests to be done at runtime. And at that point, we also decide whether to do peeling for alignment or whether we have to do a runtime alignment test with the loop version. Then we analyze the actual operations, whether we can vectorize them. And we decide after doing that whether we can do loop masking or not. And at the very end, we compute a cost and see, well, is it profitable at all? Or we ask the target, is that variant of the analysis now a better idea than the previous one that was the best? And on the basic block side, it's basically the same or similar. After the SLP discovery, we optimize the permutes. We are doing analysis on alignment and dependency. Then these are also internal data structure things. Then we analyze whether we can vectorize the operations. And after that, we basically split the pieces we found in the function that are vectorizable into pieces that are not intersecting somehow, basically. So we are partitioning the graph and costing the partition separately. So we can basically only vectorize the profitable pieces we found and do not have to. So at some point, we either vectorized everything we found or nothing, which is of course kind of stupid, right? So but now we can do better there. We can do partial vectorization of what we found. So let's try to dive into the data structures. I only have 20 minutes left. Too bad. So each instance of this kind of analysis, it has a vec.info object. The vec.info object is a base class that is derived to either the loop vec.info or a basic block vec.info thing. And the vec.info object itself, it contains shared things like the set of data references. As you saw, most of the analysis actually reuses the same function. All the same functions thing usually get only the vec.info and only needs the vec.info part. Or there, basically we have deal with this with explicit check, is this a loop vec.info, and then you see casts in the code and it accesses the loop data. And so we are not using classes and overloading for the functions, but we are basically doing manual checking in these common functions, since it's really mostly common code and it's easier to follow if we have a few ifs that depend on whether this is now loop or basic block. Right? So we have these two main objects where basically all the unordered information is stuffed in that we eventually compute and have to reuse in a second place or doing the transform phase. All the member accesses are, for historical reasons, done via macros. And I think it's visually better because it somehow stands out than having all lowercase stuff and accesses. So I like it. We try to keep it consistent. We are not fully consistent. I think there's always a few users that leak through, or some macros that were not added when adding members. And as I said, nearly all of the actual functions working on like a loop vec.info or on any type you will see later are not member functions, but they are just functions taking pointers to the relevant objects. There are some exceptions, of course. So each of the scalar statements during analysis gets a statement vec.info structure. So the vectorizer goes over all of the statements in a function or in a loop and allocates a separate structure. And it links to them via the Gimpel UID. Yeah, so you can't reuse that in the vectorizer in any other way. And we should put in there information that's specific to this original scalar statement. And members are accessed via the macros. And there are two member functions. In the v.info struct, you can look up the statement vec.info from a Gimpel statement or from a SSA definition. These are, Richard started to do C++ things in the vectorizer. So not me, the other one. Yeah. So the main data structure for the vector thing in the vectorizer is the SLP tree, which is now just a 3-letter thing. It's not necessarily super word level parallelism, but it can also be. So an SLP tree groups a set of scalar statements or has just a single scalar statement. In that case, it's not a super word, but it's a single word. But still, it groups scalar statements, and the SLP tree are nodes in the SLP graph, and the SLP graph has entries, and each entry is represented by the SLP instance object. Again, accesses to members are through macros. We have the SLP instance and the SLP tree macros. So the SLP graph, it can be cyclic, it can have multiple entries. It's basically a generic directed graph, and we only represent depends how you will call it, forward or backward edges. Basically, the edges that are there are from operation to its operands, to the operand definitions, like the SSA definition edge that's there in the SLP tree children. I think I have a slide on it. No, I don't have it, so I will talk about this. So you have on the instance, you have the root. That's the SLP instance tree. That's the SLP tree this entry refers to. Right? For example, when you have a loop and you have a store, then one of the graph entries is the store. So basically the store is an entry to the graph, and the SSA edges basically get you the flow of the SLP children graph, right? So you can, in principle, when you are not forming any statement groups, you can directly map the SSA graph to a SLP graph. So I have a second slide here. Okay, so that shows basically above the red line, we are mostly working with the statement vec info. That means there is no SLP graph yet, because we are doing analysis on the scalar statements first. And then after the red line, we are building the SLP graph with the vec analyze SLP. And from that on, all the actual analysis on can we vectorize things, do we vectorize things work on the SLP graph. So each SLP nodes, yeah, I will have an example later, I think. So SLP discovery, it's currently the same discovery algorithm is used for the loop SLP discovery and the basic block SLP discovery. I think we are now agreeing that this might not be the very best thing, but that's the way it is now. So it's basically a greedy discovery. So we, for example, start from a group of 2 stores and then follow the SSA edges. And if we arrive at compatible 2 statements, like 2 plus operations, then we make a SLP node out of them and recurse to the children. Sometimes it happens that one of the lanes is a plus and one is a multiplication. Oops, that doesn't combine. So the greedy discovery will say no, and we will backtrack, and eventually can like swap operands of 2 plus operations and hope that it will match with the next try. So we are doing greedy discovery with some limited backtracking, limited because of compile time. So for loop vectorization, the SLP build may not fail because we can't just vectorize half of the loop with loop vectorization. But for basic block vectorization, at each point we in the end decide, well, okay, we can't extend the SLP graph any further. We can basically construct a vector from the scalar SSA defs. And we hope for costing to later reject when we do this too much. So details. Here I have included a portion of the vectorizer dump details. Here you can see 2 SLP nodes, no, 3 actually. This node is for a load. So each SLP node has an operations template. That's the SLP tree representative. It's a Gimple statement. It's just there to describe the operation that is carried out, right? So it can be completely artificial and does not have to have any real relation to the original scalar Gimple. So like SLP patterns will happily create new statements there that were not there before. And it has the SLP tree scalar statements in that case. So these are the two statements we formed the SLP group from. In this case, it's actually the same. That is, we have a two-lane vector, but it's fed from the same data, which means we record for loads is also as a load permutation of a data reference group we first detect. Right? So when we do not have actual SSA definitions, we instead record the scalar ops, which in this case is a 3 and a 1. So these are just tree objects and not Gimple statement pointers. And this is when the SLP node is of constant kind. So this is denoted by the SLP tree def type, which is either internal. In that case, we have the Gimple statement definitions in the lanes, or constant or external. Constant, in this case, we see 3 or 1, and for external, that means the definition is outside of our vectorized region. In this case, like SSA definition that's invariant in the loop. Which we don't need to vectorize that, but we just have to somewhere construct a vector out of some of those, like in the prologue. And here we have a plus operation. Right, so here you can see the scalar statements we formed the group from. So we have once this SSA name 6 plus 3 and once the plus 1. And you have two children of this node. One, so we always print hex numbers, you can match them up. One is that for the load, and one is that for the constant. So the SLP graph, it contains permute nodes, and they are basically blends. The permutation is represented by the SLP tree lane permutation specification, which is, it's dumped like this. So it says the first line comes from the first child and its first lane. And the second lane comes from the second child and the second lane of that child, right? And so you can basically form arbitrary concatenation and permutation of an arbitrary number of inputs, but actually code generating, for code generation, we only can handle up to two inputs, because vectorizers can only have only two input permutations, right, at most. And here you also see that you have, when we form a group of a plus and a minus, we can do this by carrying out a plus operation on both, on basically all of the operands, and a minus operation, and then blending the vector in that way. Now you can see that in that case, there may not be an actual scalar definition for that vector lane, because it doesn't exist in the scalar program. So then we have the scalar pattern recognition phase, which is done quite early. So during the statement analysis, the scalar pattern recognition tries to see, when you have like a division statement, can the vectorizer handle vector division? And if not, maybe we can do the division by 3 by doing some multiplication and shift and or whatever, and the backend would support those operations. So we basically construct a replacement sequence of scalar statements that we replace that unsupported scalar statement. So it's completely on the scalar side. And the idea was that then later the vectorizer just can vectorize these new scalar statements just transparently, because it doesn't need to special case anything, as if it were the original scalar code. So that's what scalar pattern recognition does. It also does a class of patterns related to masking. Because when you have a bool, it can, in the scalar code, it's either a result of for example, a result of a comparison or of a bool load, but it can be used in a conditional context, or it can be used as data. And the vectorizer needs to distinguish between those mask modes and the data modes. And the scalar pattern recognition in that case basically computes scalar statements that would match up with the mask representation the target actually uses. So that's where you see like you have 32-bit booleans that the vectorizer introduces during the pattern recognition, or 2-bit booleans or something like that, because that then matches up with how the target handles this, and this allows later the vectorizer to process the data correctly. It's a little bit, I find it a little bit awkward, but it works, and nobody had the energy to come up with something better yet. I will try to skip forward. So this is just a data structure detail, how the patterns are represented. Then we have the SLP pattern recognition. So with the scalar patterns, we only looked at the scalar statements, but with SLP pattern recognition, we can actually look at the super level word groups and, for example, detect that, oh, well, we don't have to play this blend trick, but the ISA can do an add sub operation. For example, a lot of vectorizers have some building blocks for complex math operations. And those tend to mix plus and minus or lane swaps of one vector or the other. And these we can detect in the SLP pattern recognition phase. Then, as I already said, the if conversion plays quite an important role to handle conditional code in loops, and it will into the scalar instruction stream emit masked or cont internal function calls, which means we can't really use that Gimpel IL when it's not later turned into vector operations. Which, what I already said, the if conversion phase will create a copy, and it will put in a conditional that says if loop vectorized, then execute this if converted loop, and otherwise fall back to the scalar code. And when the vectorizer was successful, it will, or not, it will replace this condition with a statically one true or false condition. So basically one of the copies will be thrown away, and the if conversion will be undone when it's not needed. We also have the loop distribution path, which can do something similar and annotate the loop as dependence-free when it managed to do some extended, when it already put in runtime dependence tests for a transform that loop distribution did. Basically transferring that information into the vectorizer. Vector mask. I already talked about this. I will skip over this. Loop masking. So GCC can do loop masking. You can think of loop masking as of predicating each vector instruction with a mask that's determined by the loop control condition executed in parallel for all the loop iterations in that vector iteration. So basically, when you have the if I less than n exit the loop test, you can do this for all of the scalar iterations in that particular vector loop and generate a mask out of that and use that mask to mask all of your operations in the loop. And then you can basically elide the loop epilogue, the scalar epilogue, because in the last vector iterations, you will only execute a subset. So you will only have a subset of the vector lanes enabled that way. and that handles basically the tail of the loop that usually you would handle with the scalar epilogue. It requires a vectorizer that can do masking on more than just loads and stores usually, because like when you have a vector division or floating point anyway, which can trap, you have to mask also like an add. Yeah, so the main analysis of the of whether we can vectorize something is in the vectorizable operation conversion, shift, load store, and so on, functions in the two-vect statements. And originally I planned to walk through the vectorizable operation thing, but that's no longer possible, I think. But that's the simplest one. So if you want to have an idea how it actually works, that's the one to look at. The others are all complicated because you can see the operation is the canonical case and everything else is special cases because shifts are different or loads and stores are different anyway. Yeah, vectorizing loads and stores. We skip this. Transform phase. So the only special thing of the transform phase is that only at that point we are actually doing any CFG manipulations. So the vectorizer before that does not modify the Gimpel IL in any way. If conversion did, but the vectorizer itself does not. So only when we commit to actually vectorizing something, we are changing the IL. We are doing the loop copying for the epilogues and the prologues, and we are inserting the vector statements. We remove the scalar statements with side effects, and all the rest of the scalar statements get elided by that code elimination later. So we are not bothering to clean up there. Yep. Debugging. There are debug overloads for SLP tree and SLP instance. That's unfortunately it. You can call the .slp tree function, which puts out some graph width .file, so you can visualize it. I've not used it very much. It helps for SLP pattern detection, for example. So when you try to visually match up how does this graph look like. Otherwise, I think the details vect tree dump is very good in pinpointing what goes wrong, but it's very verbose. So you need to learn to filter. Yeah, always use grep. So for example, when the dump tree vec details says unhandled data reference, we then grep for unhandled data reference, and then you find the place where it emits that message. Then you can set a breakpoint there, and you can inspect data, basically. So that's how I work when trying to understand how things do not work. And the test suite is your friend, even if the coverage is not too great, but it's good enough that when you hack in the vectorizer, you only execute the vect_exp part, that you usually catch the very big issues. When you are working on more target-specific features, you have to enable some ESA features or run the target-specific tests. I think SVE is quite extensively tested. The RISC-V stuff as well. On x86, there is not much target-specific tests, so you really have to like enable AVX or AVX 512 on the vect_exp test suite part. Yeah, I think I'm at the top of the hour, unfortunately. If there are any questions, I can be catched in the hallway or at dinner, or try to catch me or write questions on the mailing list. Post patches, eventually you will get a review from Tamar. And I'd say, yeah, have fun with the vectorizer. It's really fun. Try to not do too complicated things first. Unfortunately, all the simple things work already. But yeah. So thank you. There is a question.
Hi, thank you. This morning we presented a proposal to introduce lane support in GDB. The focus there is highly GPU oriented, but the idea is not really. I mean, it would apply to vectorization for CPUs as well. The thing is that if the compiler generates some debug info, let's say for a block of code, it introduces in Dwarf that the block is vectorized and the length of SIMD is this and that. GDB would, and also the locations in Dwarf would have to include some lane specific operators which are coming into Dwarf 6. Then debugger would be able to allow the user to debug the vectorized code, switch between lanes. Let's say there's a vectorized code, I mean print the value of I, and so on. And you showed something about lane masking, and I believe it also plays well with this model, because then by looking at the lane, loop masking, by looking at the loop masking, the architecture in GDB would be able to say, okay, these lanes are now active, these lanes are inactive, and so on. So I just wanted to comment on this.
Yeah, I think Hansa also mentioned that the auto FDO is confused by vectorized code because it makes it look like the scalar loop iterates not very much anymore. Mm-hmm. And it's not reflected in the debug information. So in fact, the vectorizer throws away all debug statements because, of course, they make no sense in the vector loop. So we have to come up with something which it seems it's kind of, there's a possible solution for the Dwarf side, but we still need to represent it somehow in the GCC debug statement side.
Yeah, it's not part of official Dwarf yet. It's upcoming, but I think there's a good opportunity potential there.
It's an area that definitely needs improvement.
Yeah. Okay, thank you.
There's another question.
How the costs are assumed? We consider that all the vectorized math routines are always beneficial compared to scalar routines. And especially when we have different variants of the math routines, how the costing plays a role, how it is costed.
So it's the target responsibility of doing something there. So there are basically two ways to get vector mass functions. One is by having a declaration annotated with the OpenMP SIMD attribute. There, GCC doesn't have any idea of how good the implementation is. Of course, GCC simply assumes that it's not worse than executing the same function n times as scalar code, because otherwise it wouldn't see the declaration, or otherwise the function wouldn't be available. So
it also depends on the runtime values, right? Internally, the math library routines, vector math library routines, they also call these scalar variants, right? So even the glibc mviclib also has calls to the scalar variants from the vector library routines. So that means like the casting that we are doing in the compiler side can go wrong, right? So.
Yeah, sure. I mean, it's always only a guess, right? You never know whether it's actually profitable or not. But I think it's a good guess that if there is a vector version of a function and you can use it, that it's going to be better than not vectorizing at all. because that's the only other choice that's currently implemented. So what the GCC vectorizer doesn't yet do is when you vectorize a loop and you run into a statement, if it's a call or another statement, that we just emit that statement n times and first decompose the vector and later build it up again. We could do that, but it's unlikely to be profitable, which is why we haven't implemented that yet.
Yeah, thanks.